My name is Melissa Russell. I am part of a research group at Imperial, in charge of designing the ultimate wind turbine. We are close, but I fear for my life. We are being followed by the gas and energy companies that are trying to maintain their dominance by destroying any evidence of our project. I'm uploading a video of our first design so that the world can see that there's a better way. Should anything happen to me or any of my friends, our objective was to maximize the power generated by the turbine while minimizing mass, to make for a cost-effective design. The first decision that was made was to opt for a two-blade design. In order to print a one-piece model of the turbine, the length was limited to 400 millimeters.
The first part of the process involved selecting an airfoil. We needed an airfoil which had a high lift-to-drag ratio. In the end, we selected the SG6043. We also needed to choose a TSR. After consulting multiple sources on the web, we found that a TSR of around 6 was most appropriate for a two-bladed wind turbine. However, the article also stated that despite designing for a certain TSR, TSRs achieved in testing could often be much higher than this. Bearing this in mind, and also wanting to keep the RPM below 3000, we decided to offer a TSR of 4.2. The next stage of the process was to find the chord and twist distribution of the blade. You have to twist the blade in order to maximise efficiency. There are a few ways of doing this. Vets assumed a constant angle of attack would be optimal, and hence found a chord and twist distribution accordingly. We felt that the constant angle of attack would have an advantage, constant circulation and hence lower induced drag, at least at high TSRs. Schmitz optimises power for a section of the blade by finding an expression for an element and finding the twist which maximises it. Both methods produce very similar results for twisting chord at higher radii but differ significantly at the root. We felt the Schmitz distribution was more accurate because it accounts for interference with the wake and Betz does not. We therefore decided to use the more accurate Schmitz distribution as we felt it gave a better representation of the aerodynamic effects. Before moving forward, we decided to use Cubeway to provide a crude estimation of CP and ensure there were no fundamental errors in the design. We also decided to decrease the chord length of the root as we felt that a smaller chord length would be fine for structural integrity. We also decided to increase chord lengths close to the root in order to improve the chance of self-start. We verified this in a MATLAB analysis, which showed that there was a non-negligible torque at a rotational speed of 0 revs per second. However, this does neglect the moment of inertia of the core inside the generator, which would slow the angular acceleration, and also frictional moments which may stop this angular acceleration altogether. A simplified structural analysis was conducted in MATLAB using basic cantilever beam and torsion theory. This was made possible by calculating a series of span-wise aerodynamic loads. The main difficulty in doing this was finding the second moments of areas of the individual cross-sections, as well as their torsional constants. In the end, a function called polygeon was used, available on the MathWorks website, to find the second moments of areas, Y centroids, etc., of the cross-sections. The torsional constants were more difficult to calculate, so we used a worst-case scenario ellipse to model them. In the end, a deflection of 2 mm at the tip was found, and a twist of only 0.2 degrees, ensuring that the blade wouldn't twist into stall during testing.
This script also allowed us to calculate the stresses in the blade, found by superimposing the centrifugal force on top of the aerodynamic loads. These were deemed to be the most significant forces acting on the blade. The stresses were found to be well within the yield stress of the plastic ABS. However, we deemed the structural integrity of the blade to be of great importance and decided to test it on clear parameters as well. Finite element analysis would give a much more reliable view of the stresses in the blade. Significant loads were placed on the blade in Korea. We tested it at the maximum wind velocity of 12 meters per second and the maximum angular velocity of 3,000 revs per minute. It was found the root stress was too close to the failure stress of ABS, and since this method was still approximate and we did not have all the real loads involved in the simulation, we opted not to take the risk and to instead use a thicker airfoil at the root. Since using a completely different airfoil down the whole blade would lead to losses in CP, we decided to try and find an airfoil from the SG60 series, which can be blended into SG6043. After trying 6042 on the root with similar results, we decided to use 6040. As this solution significantly reduced the maximum stress, we were now well within the yield stress of the plastic ABS.
A great deal of thought was dedicated to the design of the blade tip, as a poor design would significantly decrease the overall blade efficiency, and with such massive potential efficiency gains, a good tip design is a must. Various iterations of the tip, such as simple side tapering or a curved finish, were considered, as well as their effect on the power coefficient. We were looking for a design that primarily mitigated the effect of tip vortices, but also increases the power and the efficiency. Both the Horner tip and the Shark tip mitigated the effect of vortices as they increase the effective wingspan of the aircraft as the formation of vortices is delayed and moved horizontally outwards from the center, resulting in a decrease in downwash and reduced drag. Both tip designs are very similar, but given that most of the applications we found for the Horner tip involved static wings, we decided to opt for the Shark tip instead, which is heavily considered and tested in relevant wind turbine applications, and hence thought to offer the best design. For an effective Shark tip, the trailing edge needed to be as thin and as sharp as possible, whilst maintaining a rounded edge, with a sharp corner. The sweep and rake angles were studied from the extent of material available, and a sweep angle of 15 degrees was chosen. This was then molded by two ellipses to provide us with the chord lengths and positions for the airfoil sections. A smooth finish is also required for maximum benefit, but it was also a challenge to input that in cryo-parametric and to manufacture, but worth the time dedicated to it as it should positively impact our power output.
The priority when designing the cone was for a design that didn't detract from the performance of the blade, but guaranteed a durable structure. In order to minimise material, the cone took the form of a hollow cylinder with a curved nose placed over one of the open sections. After investigating the benefits of elliptical, parabolic and ogive shapes, a Hack series formula was used to determine the shape of the nose as its shape minimises drag. A single cone, comprising of both the cylinder and nose, was then created in cryo-parametric before the finished blades were attached. Attention then turned to the hub, a crucial element as it transfers the torque generated by the wind turbine to the mounting shaft. Clearly an interference bit was required, but to absolutely ensure there was no slip between the two surfaces, slots were cut in the hub and extrusions made on the inside of the cone for an extra snug fit. These slots had the added benefit of minimising the mass of this added metal component. Finally, we reduced the length of both the cone and hub by 10 mm from the maximum permissible length to save weight but maintain good contact with the mounting shaft.
Once the design was completed, manufacturing began. To make the hub, we started with a solid aluminium cylinder. We used a lathe to drill the hole in the hub on which the turbine would be mounted. A CNC milling machine was then used to cut the slots from the hub to increase the grip between the hub and cone. To refine the imperfections of 3D printing, the turbine was sanded to ensure a smooth finish and to remove the excess material that was added to ensure a smooth trailing edge.
Testing was the moment of truth for our design. The turbine was placed in the test section of the Donald Campbell wind tunnel and brought up to speed for wind velocities of 6, 8, 10 and 12 meters per second. The generated power was then measured. Despite it coming very close, the turbine was unable to self-start at 10 meters per second without a small perturbation. We suspected this could have been the case as the dimensions of the 3D printer limits the length and hence the surface area of the blades. These limitations make it very difficult for the standard blades to produce a non-negligible torque at low RPM whilst producing a good power coefficient at high RPM.
The wind turbine produced a power output of approximately 13 watts and had a coefficient of power of 0.104 out of a realistically possible 0.35, giving us an efficiency of 30%. The maximum power output occurred at a much lower RPM than expected, and so there is clearly more energy that could be extracted from the wind.
This issue is thought to be mainly due to an oversight, the magnet script, used to generate the twist angles to be inputted in the code. The inputted angle should have been beta only. Unfortunately, due to a miscommunication, the inputted angles were alpha plus beta. This led to lower angles of attack over the whole blade, and thus to the reduction in power generated, torque, and RPM. However, this additional twisting increased our chances of self-starting, since the cross-sections near the tip were originally untwisted, and thus, by simple conservation of momentum, more torque was generated at no rotational speed. To reduce the mass, both the hub and the core can be made shorter and thinner. Another important element to minimize is drag. To do so, the cross-section area of the wood can be reduced, and a circular wood can be used instead of the airfoil one, such that it acts more as a bluff body. Manufacturing also induces errors. To investigate these effects with the help of Mr. Grant, a laser measurement analysis of our model was made and compared to original CAD design. It was found that the twist angles differed by a maximum value of 1 degree, and that our core distribution was close to the one expected. To limit these effects, bead blasting can be used to remove excess material, and vapor smoothing can be used for a better sanding. Rectifying the twisting of the blade and implementing these improvements would vastly improve the performance of the blade, which would lead to a wind turbine design that will revolutionize the energy industry through the supply of cheaper power.